On this first slide, think of blast furnace exactly like a car engine. When the engine is dead and cold, a normal key starts is not enough. You need jump cable to give a short powerful energy surge and bring it back to life. A cold blast furnace is same. After shutdown, the furnace is like a dead engine. The cohesive zone is frozen, the burden is stiff, and gas channels are blocked. Normal burden charging cannot immediately restore the thermal state. A coke blank, a layer of 100% coke without ore, works like thermal jump cable. Because there is no ore to melt in that layer, all the energy from the tuer goes into reheating the frozen zone and reopening gas passage. So the simple message of this slide is coke blanks are not just more coke. They are focus thermal tool, high intensity heat delivered fast, exactly where the furnace is frozen. Now the science why pure coke works. Now what is the science behind this? On the left you see the problem in a cold furnace. The cohesive zone has moved down too close to tuer. The layer is frozen and thick. The gas channel are blocked so permeability collapses. Under this condition a normal ore coke burden simply doesn't melt and flow. On the right is the solution, a pure coke blank with no ore is that zone. There is no melting duty. Even kilocalorie released at the two-year raceway is free to heat up and lift the cohesive zone. The coke layer itself is highly permeable, so it immediately creates clear gas path upward. The outcome is faster recovery. A change in normal coke rate might need about 10 hours to shift the cohesive zone. A properly positioned coke blank can restore the zone in about 6 hours only. So the key takeaway from this slide is a coke blank works because it changes where the heat is consumed directly into frozen zone, not into melting fresh ore. That is why it is so much faster and more reliable than just increasing coke rate in burden. Now this slide answer a very practical question. How much extra coke do we need? From operational experience, the required extra coke is proportional to shutdown duration. For plant stop, we use approximately thumb rule for 1 hour stop about 2 tons of extra coke for 6 tons for 8 hours about 8 tons for 12 hours about 10 tons for a 24-hour stop about 16 tons for 24 to 48 hours about 24 tons. Then there are two critical export rules. The hearth volume rule. Ideally, the total coke blank volume should be greater than the hearth volume. If you use only half hearth volume, statistics say the recovery is much more likely to fail. Wall placement and timing. If we consider extra coke should be placed at the wall because the foot of the cohesive zone at the wall is the most critical for stability. The first coke blank must be located in the mid wash exactly at the moment you stop the furnace so the heat is available immediately on restart. The historical example at the bottom makes this real. On 18-15 feet furnace, operator used about 13.6 ton as a first blank, then light ore charges, then another 9-ton blank and achieve a successful restart. For a 10-week banking, a huge 75-ton fuel blank was used to maintain a thermal reserve. So here is the message is pretty clear. Quantity and geometry matters. Enough coke at the right volume in the right place. This slide explains how charge coke blank in three phases. Phase 1, uh, that is the pre-stop banking. Before stopping, you start building a heavy coke blank. You continue normal ore coke layer but with a strong emphasis on coke so that a thick coke band is created inside the furnace. Over 8 to 10 hours, you watch your brightness increases. That tells you thermal energy is being stored in the burden. Phase 2, at blast stop, the timing is critical. When you finally set off the blast, you want the second coke blank sitting in mid Bosch region. The first blank is already descending and supporting the hearth, while the second blank is positioned to act immediately when you restart the furnace. Phase 3, during shutdown, in long blank, the stock settle roughly 2 feet per week is typical. That settling creates empty space at the top. You must refill that space with fresh coke before starting. Otherwise, you create air pockets and poor gas distribution. The top view sketch shows why we place the extra coke at the wall. That is where the cohesive zone hang and where support is most needed. So for this slide, the message is coke blank are not just a single batch. They are planned three-phase charging strategy with careful timing and wall side placement plus regular refilling if the stocks settle during long banks. So finally, this slide walk through what happens after shutdown. When you restart the blast and rely on that cook blank, the restart sequence is in 4 time blocks. Our zero blasts to restart. You restart at around 50% blast and then slowly increase towards normal. You watch the 2 years flame closely for any abnormal behavior. Hours 1 to 2 thermal climb. The coke blank now sitting near the 2 years burn very intensely. Temperature rises quickly, giving a strong thermal push into the frozen zone. Hours 2 to 4 cohesive lift. The cohesive zone begin to melt and move upward. A key indicator is silicon content in hot metal dropping from around 0.8% towards 0.6%. Gas flow normalizes and slag fluidity improve. Hours 4 to 6 is normalization. The furnace return to a stable thermal state. You resume the normal ore coke ratio and full hot metal production. This slide also shows the success indicator: bright, uniform 2-year flame, rising top gas temperature in the early phase, silicon trending down to the normal band, slag flowing freely, stock rod descending smoothly, and failure indicators like silicon staying above 1%, a stock rod not moving, slag is sticking or poor tapping, abnormal pressure rise. If you see these failure signs, the strategy is ready. A, a second coke blank is already planned. Uh, so charging that second blank can restore the thermal state within another 2 to 4 hours. So the closing message is a well-designed coke blank strategy gives you predictable step-by-step restart path with clear signal for when the furnace has recovered and backup plan if the first attempt is not